If you drop a glass, it shatters. The drop happens first, the shattering happens second. That strict sequence, one event cleanly triggering the next, is the absolute rule of the macroscopic world. We build our entire understanding of reality on this unbroken chain of cause and effect. It is how human intuition functions, how we structure logic, and how we experience the forward march of time itself. The titans of classical physics, like Albert Einstein, cemented this rigid determinism deep into the scientific method. They prove that the universe operates on a strict set of rules, where the past always dictates the future. If you can prove that sequence false, if an effect can somehow happen before its cause, the entire framework we use to understand the passage of time collapses. But when you zoom past the macroscopic objects we interact with every day, down into the microscopic scale of quantum mechanics, those rigid rules dissolve. Over a decade ago, physicists began testing entangled photons, sending them through devices where they could navigate as either a particle or a wave. The data showed something unsettling. Measuring a photon after it had already cleared the device actually forced it to behave as a particle or a wave during its journey. The measurement reached backward in time to dictate the photon's past behavior. This challenge to classical physics suggests that strict cause and effect is an optional macroscopic illusion rather than a fundamental law of nature. Physicists have a specific term for this breakdown of sequence: indefinite causal order. You might already be familiar with standard quantum superposition, the proven reality that a single particle can exist in multiple physical locations at the exact same time until it is observed. This animated diagram shows how we can apply that exact same logic to the flow of time itself. Instead of two physical locations, imagine two timelines. In one, event A causes event B. In the other, event B causes event A. Under indefinite causal order, both of these sequences happen simultaneously. The true sequence of events doesn't actually exist yet. It remains a matter of pure probability, floating in an indeterminate state, right up until a measurement forces reality to pick a lane. Within this temporal superposition, the linear arrow of time vanishes. Past and future lose their strict definitions, leaving only a fluid smear of possibilities. To figure out if this temporal superposition was a physical reality or just a mathematical quirk, researchers at the University of Vienna set out to build a highly specific test. They designed their test around Bell's inequalities. In physics, this is the mathematical gold standard used to determine if weird quantum behavior is genuine, or if there's just some hidden classical variable dictating the results. The team generated a pair of entangled photons and routed one of them directly into a highly specialized testing device. This diagram illustrates the core mechanism of the device. The photon enters a logical loop where its quantum polarization alone dictates its path. It either experiences manipulation A first, then B, or it experiences B first, then A. Because the two photons are entangled, researchers can measure the polarization of the second photon. That measurement retroactively determines the specific path the first photon must have taken. This entire setup acts as a strict mathematical trap. If causality is absolute, and events must happen in a specific order, the final measurements are forced to obey the rigid limits set by Bell's theorem. So, when the researchers tallied the final correlation of outcomes, what did the data actually say about the timeline of these photons? This graph plots the experimental results against our classical expectations. The data violated Bell's inequalities by an extreme margin, 18 standard deviations. An 18 sigma event represents a statistical impossibility. It rules out the chance that any local hidden variables are responsible for the outcome. The data provides undeniable empirical proof. The superposition of temporal order is a verified structural feature of quantum mechanics. But modern physics demands extreme skepticism. Before we declare the death of linear time, we have to acknowledge that this experiment still has technical loopholes to close. The most significant is the loss loophole. During the experiment, roughly 99% of the photons sent into the device are lost before they can ever be measured on the other side. This leaves open the possibility that the lost photons might contain exactly the data needed to restore a classical, cleanly causal timeline. Even with those necessary caveats in place, the sheer scale of this anomaly is too large to ignore. Science can no longer blindly trust the assumption that events must unfold in a straight, linear sequence. Zooming out from the laboratory, the question becomes one of engineering: how to build technology that functions within a timeline that loops back on itself. It turns out, abandoning chronological order is highly efficient. Processes that utilize an indefinite causal order can vastly outperform traditional causally ordered systems. This phenomenon enables a range of functions, from advanced noise mitigation and channel discrimination to ultra-secure quantum communications. And this is the hardware where these timeline-bending processes will actually take place in the near future. By proving that strict cause and effect is optional, physicists have established the architectural blueprint for hardware that operates entirely outside of chronological sequence.